Hey guys, welcome. Yeah, so example 1 on the Weirstrass substitution. But yeah, if you have not watched example 0, then you should pause this video right now and first watch example 0, because there we look at the Weirstrass substitution big picture and we explained why and how it works. And at the tail end of example 0, we actually already had our first example when we did the integral of sec x dx using the Weirstrass substitution. So technically this is your second example, yeah? Okay, but the bigger reason why you should watch the example 0 is because, we said that the Weirstrass substitution always starts with this, and we said this in example 0. But yeah, by starting here, we figured out what dx has to be in terms of u, and we figured out what sine, cosine, tan, cotan, secant, and cosecant all have to be in terms of u by beginning with this substitution. We did all that in example 0. So then you could use all of those things that we came up with in example 0 instead of reinventing the wheel, yeah? All right, in fact, I even flashed this integral at you in example 0, and I said that we're going to do it because we're going to do it in a future example because, the reason why I flashed it is to show you that the Weirstrass substitution is useful for integrals involving quotients of trigonometric functions, which this is, yeah? Okay. Enough said. So let's get on with it. From the work that we did in example 0, we know that dx, by beginning again with the substitution that u has to be tan of x over 2, we came up with the fact that dx will then have to be 2 du over 1 plus u squared. And we also said that from this, sine x has to be equal to 2u over 1 plus u squared. All right, so good, we did all that work in example 0, huh? So here we just plug this in and that's how we start. So like dx is, I could put the 2 right here, but otherwise it's du divided by 1 plus u squared, right? That's dx. And then we need the 2 plus sine x. So we have 2 plus sine x is right here. That's 2u over 1 plus u squared. Now you should see that I could, first let me be careful. That's a parenthesis right there. Not happy with the second parenthesis. Let's do it again. Yeah, okay. But yeah, you should be able to see that there's a 2 I can factor out from the denominator. How nice. Because this turns into a 1 and yeah. And then now I have a 2 over 2 here, and so I could just cancel that. And also, I would like us to understand that this here is multiplying this parenthesis. So what we can do is distribute it to here and here. And if we do, this is just like me, with my good memory. Otherwise, you can erase it. Yeah. Okay. So then we have du over. And then once we do the distributing, we get 1 plus u squared here, and then plus, right? Plus, when we multiply this here to that, we just get a u, right? Okay, cool. So that's better as u squared plus u plus 1, u squared plus u plus 1. And we see that to make more progress on this, we need to see it as a perfect square in the denominator, perfect square binomial plus a constant, because we're going to go with the tan inverse idea, right? We're going in that direction anyway. So we have this. Now these first 3 guys, they make the perfect square u plus a half squared. So u plus 1/2 squared plus 3/4, right? And then I could take out a 3/4 from the denominator, because if I'm going to do tan inverse, I want that to be a 1. But yeah, so that amounts to writing 1 over 3 over 4 here. But then that means this is a 1. And since this guy did not have a 3 over 4 that we can factor out of it, we could just divide it by 3 over 4 to compensate for writing this here, right? Okay, now dividing by 3 over 4 is the same as multiplying by 4 over 3. So we'll reckon that there, and here also 4 over 3, right? Okay, and furthermore, I want this here to go inside of the parentheses, and I could do that. And I could do that by writing this 2 over root 3 times u plus a half, like that, and then o squared, right? So what I just wrote, this here is the same thing as this here, right? And I prefer this version. So I'm gonna replace this here with what's here, but I'm also gonna do one more thing, which is distribute the 2 over root 3 to this and that. And so I'm gonna get 2u over root 3, and then plus I'm gonna get 1 over root 3. I'm not gonna forget to square it. Yeah, what I have here is identical to that. Right? Okay, cool. So next I go, oh yeah, I go like let t equal 2 over root 3 u plus 1 over root 3. Then that means that dt is equal to 2 over root 3 du, meaning du is equal to root 3 over 2 dt, right? Okay, so I go 4 over 3 times root 3 over 2, and then dt. So root 3 over 2 dt, that's du, and that's what I just wrote over here, right? Okay, and otherwise over t squared plus 1, which is the same as 1 plus t squared, right? Okay. So we can now go like this. So it's 2 root 3 over 3. So 2 root 3 over 3 integral dt over 1 plus t squared, right? Okay, so that becomes 2 root 3 over 3 tan inverse of t plus c. If only one of us can remember what we said was t. Well, lucky for you, I remember. I think I do. 2 root 3 over 3, and then tan inverse of what was it? 2 over root 3 u plus 1 over root 3, and then plus c, right? Okay, what do I have left to do? I have left to do replacing this u with what it is. And what it is that since the Weirstrass substitution starts like that, this u is really tan of x over 2. So yeah, tan x over 2 plus 1 over root 3 plus c plus c.